All right, howdy everyone. We're continuing our lecture on topic 2, vision, and section 2.5 is about this concept of visual acuity. And so when we test your vision and you say I can see 20/20 or I see 20/30 or 50 or 2200, that's a measure of your acuity, your ability to resolve detail at distance. And there are thresholds that we want to think about for how large does something need to be seen by somebody with various degrees of acuity. Seen at all and seen with enough detail to recognize what it is are two different thresholds. Okay, so first of all, probably everybody has experienced one of these tests before, whether it was, in school growing up or whenever. But you get tested to see, how well your visual acuity is according to or relative to a standard. And that standard we define is 20/20. And in this lecture, we'll talk more about what that means, why 20, what's the 20 about. And just know for now that our standard measure of acuity, basically what we say is our comparative value is 20/20, and that's this underlined red line here on this tool, which we call a Snellen chart. So named after someone named Snellen. And essentially what you'd do is you'd stand a predefined distance away, and in fact, I just saw this the other day when my son was doing a driving test. They ask you to read as far down as you can still resolve the characters. If you've ever had an eye test, this would be a similar, like at an ophthalmologist, that'd be a similar sort of test. Now, it's not the only one, the Snellen chart. There are also E charts, and so you'd go, talk about the orientation of the E. If you can't resolve enough detail, these would just look like squares. It'd be hard to tell which way the E opens. Similarly, other patterns, gradients, and you identify, well, I still see shapes versus it all kind of blends together into a gray. But the Snellen is the most well-known, most well-practiced type of assessment. All right. This is a huge approximation, so just bear with me here, but just to show you a little bit about what it might look like if you had acuity at these different levels. So if this is 20/20, this is our standard level of acuity. I can't read, the signs that are on this building, but I can see fairly crisply at a pretty decent distance. This would be about 20/50, just as an approximation. Now, it's not perfect, right? It's just an approximation here, but 20/50 is a legal acuity without glasses. If you see 20/50, you can drive legally in the state of Texas. So 20/50 is the requirement to be able to drive without glasses. If your acuity is worse than this without glasses, then on your driver's license, it would likely say something like must be wearing corrective lenses. 2200, this is about where they start saying this is legal blindness. Okay, so it's not true like medical blindness, as in there's no light, that's being processed by the eye, but the acuity is there's so much refractive error, right? The acuity is so poor that you can't make out enough detail to effectively see more than in your hand in front of your face. Okay, so I get patterns of light. I could see if there's something moving, but to resolve detail, this would be technically legally blind. And my visual acuity when I was a child was this and worse. So I know in terms of dioptric power and in terms of refractive power, and in some of my historical prescriptions, it was like -11 and -13, which I didn't do the math, but it was legally blind. All right. Okay, so visual acuity. So acuity in everything we're going to talk about in this class is always expressed as 20/20, 20 blank, right? 20/ another number. It's formally defined as the ability to resolve detail. And it's typically associated with how much subtended visual angle does the object you're trying to see and recognize, how much yes, basically how much visual angle does it subtend? So this is what we mean. This is a subtending, and it goes from here to here. And so in terms of how much space on the retina, or in terms of how much of the retina is used to process that image, we're going to talk about the visual angle. Okay. Now, if I see 20/20, so there's a big caveat here. We're going to start by talking about the standard vision, and vision can be better than 20/20. Can be considerably better, actually. My wife sees better than 20/20, but 20/20 is still our standard. So we're going to talk about all of these thresholds relative to 20/20, and sometimes we may need to make corrections from the 20/20 standard to a different acuity, okay? And that matters for things like driving in the state of Texas. What can we assume about the acuity of the drivers? Well, they're at least 20/50, okay? All right, so if I am a 20/20 vision, that's my standard. Another way to characterize that level of acuity is something that subtends 5 minutes of arc. This apostrophe here is what we use for minutes. The total height or the total width of the character, whatever the dimension is that you're subtending. If that is enough for you to see the object with enough resolution to know, okay, there's at least a box there, then that's one way to define 20/20. The other is the stroke width. So the ability to resolve detail, as in see that there's a line there or that there's not a line there, needs at least 1 minute of arc. So a fifth of the distance for the entire shape is the size of the amount of detail that you need. So this thickness right here, the thickness of this lettering needs to be at least 1 minute of arc if I'm 20/20 for it to be visible at all. Also, this gap needs to be at least 1 minute of arc so that I see there's a gap. Otherwise, my eyes are gonna, not see a gap there. It's gonna be like a continuous filled shape. Okay. Good, yes. So that's how they tune these sorts of Snellen charts. Basically, if this is what a 20/20 person could just barely make out, then 20 feet away, okay, that's where the 20 comes from. At 20 feet, I'm standing 20 feet away. Here's the chart. Here I'm standing. I should be able to just make out this line. And what I should assume, if I'm a 20/20 acuity person, is that the height and the width of each of these letters subtend at least 5 minutes of arc, and the stroke width and the gap width is at least 1 minute of arc. So those are our big thresholds: 5 minutes of arc, 1 minute of arc. However, only if the person is 20/20. So we're going to have to do some conversions. Okay. All right, so here's our 20/20 Joe standard. Okay, so I may accidentally call him Stanley standard. That kind of like that flow a little better, but I got this guy with the average Joe. So here is our 20/20 avatar. Okay, so this is, this person sees average or as our standard, I should say. All right, so let's, we got these three objects. We can see them with enough clarity at these distances. Let's say these distances, this is right where I can still make it out just nicely. If I go a little bit further, they're starting to blur. But I can see them with a certain clarity at each of these distances. So let's say George now is 20/50. So he does not see with as much clarity at the same distance as Joe's standard, okay? So at 15 feet, 20 feet and 50 feet, these same objects, if they're at the same distance, they're gonna look blurry, okay? And so if we wanna be able to resolve the detail with these, for George, who's 20/50, oops, I gotta move everything closer, okay? So, oh wait, what about this? If I move that watermelon from 50 feet to 20 feet, suddenly it's just barely clear enough. In fact, George, here we go, get ready. All right, George will see this watermelon at 20 feet with the exact amount of clarity. The acuity brings clarity and detail. So the same amount of clarity that George can see of this watermelon at 20 feet, Joe Standard can see that same watermelon at 50 feet. And it's not a coincidence that Joe Standard is 20/20 and George is 20/50. And I'm talking about distances of 20 and 50. That is where those numbers come from. So I've got some slides here where we're going to break that down, derive it, give you some references to go to so you can understand this. But that's where 20/50 comes from. Okay. Now let's say we got Hawkeye and he's got better than 20/20 vision, just like my wife after her LASIK surgery. She sees about 20/15. So what does this mean? It means Hawkeye can see at the same distance as Joe Standard. He sees with as good or better, but also he can move things further away. And so what Joe Standard sees at 15 feet, that same clarity can be achieved by Hawkeye at 20 feet. And again, notice 20/15, 20 feet, 15 feet. That's where that comes from. Okay. All right. So I hope that made sense. If not, we got some more examples. All right. Well, hey, Joe, if you move that strawberry back to 20 feet, he doesn't see it as clearly anymore. So again, remember that Hawkeye's got better acuity than Joe Standard. And eventually, even though Joe Standard is 20/20 and we think, oh, that's really great vision, it's not perfect vision. It's just the standard that we set. And so Joe's, things will get blurred out when they go a certain distance. It's just that Hawkeye can resolve things over a greater distance than Joe Standard. All right, here we go. So here's the cheat sheet, and we're going to come back to this a few times. So let's assume that this letter and this letter are exactly the same. So this is the watermelon, and that's the same watermelon, okay? But we have two different people who are viewing this item, this watermelon or this letter, and they're viewing from different distances, okay? So let's take Stan. I'm sorry, I said I would do that. Joe Standard, aka Stanley Joe Standard. Let's call him that. Joe's his middle name. So he's got 20/20 acuity, okay? So let's just say he can see this shape, he sees it well enough to know it's an E, and it subtends a certain visual angle, and we know we need at least 5 minutes of arc in order for that to be visible at all for someone 20/20. So we hope it subtends at least that much, right? So let's say he can see it, then we know it's at least 5 minutes of arc, and he determines he can see that thing from X feet away. Why that matters? This X, if you take that same value and you put it here and you identify a person who is 20X, so could be 20/50, right? Could be like George here, could be 20/50. What that means is at 50 feet, your standard, Joe Standard, will be able to see this object with the same amount of clarity as a 20/50 person will be able to see at 20 feet. So again, that's where those numbers come from. The person who is 20/X, the easiest way to do this calculation, the standard is have them stand at 20 feet and then have Stanley Standard Joe Standard move around until it gets a certain level of clarity. And then if you have the same clarity in this viewer, that's how you can calculate their acuity. You can also then use, if you know each person's acuity, and you either know the distance or the height of the object, now we can start equating things. We can start using trigonometry. We can start using some approximations and do a number of calculations to determine how far away something needs to be, how large it needs to be, or what sort of acuity in the person do you need for them to be able to view that object. Okay. All right. We're going to start talking thresholds here pretty shortly, but I've already highlighted the threshold of detection. This is, do I see something at all, or is it not large enough to even register in the density of my retinal network? It must be at least 1 minute of arc. That's the same thing we talked about with the stroke width of the letters, because if it's not at least 1 minute of arc, then it's like there's no line here or there's no gap there. So you need to have at least that much subtending in order to recognize, like, think of that as like the difference between two retinal cells versus only one processing that square area, okay? Getting to 5 minutes of arc, if I'm 20/20, that's our threshold for recognition. So if it's 1 minute of arc, I can see, okay, there's something there. I don't know what it is. It's too small. I can't make it out. If it's 5 minutes of arc, you could say that's an E. Okay, I can see just barely that that's an E. So we've got our threshold of detection. Do I see something at all? And our threshold of recognition. Do I see it with enough detail that I can recognize what it is? Those are our two thresholds that we need to think about in this topic. Okay. So again, this relationship here, I hope you can come back to this slide and then, do a little mental math when you need to, and remember this relationship, and you should be able to solve most of the problems that go with this, with this technique. Now, I've already derived it here, but we're going to go through the derivation a little later. But recognize that there is a relationship here between the ratio of these two angles, right? So this person, whatever their acuity is, there is a subtended angle. Doesn't matter what x is, this theta will be constant if this distance is constant and this size doesn't change, right? We may need a certain angle to be able to see it. I'm not saying if this person can see it or not. I'm just saying how much subtended angle does this object subtend at 20 feet? All right, so if I know this angle, and I know this distance and this distance, those two are proportional. So theta 1 over theta 2 is proportional to this distance over that distance. I should say distance 2 over distance 1. Okay, so that's where this relationship comes from. So this is also going to be something we're going to want to use. And all of this depends on that assumption that this object is exactly the same as this object. If I'm looking at two different letters or two different sized shapes, then this whole relationship doesn't work. So these must be the same object. All right, so this is a bit of a recap here, but if we are Joe standard, we see 20/20, then our threshold of detection is 1 minute of arc. We need at least 1 minute of arc of gap. We need at least 1 minute of arc of stroke width in order to see any shape at all here, okay? If it subtends 5 minutes of arc, that's enough for us to recognize it's an E as opposed to just a blob or a dot, okay? So we need to get at least that much subtended angle to recognize a complex shape. All right, so that's 20/20. Now, if I'm 20/40, what does that mean? So now I don't see as well as Joe standard. Things that are further away are blurrier to me, but by how much? And as it turns out, by twice as much, okay? So again, just like this, let's go back to this here. Theta 1 over theta 2 equals the ratio of the two distances. And if we talk about a 20/20 or a 20/40 person, we can plug in the 40 person here. So we can have 20/40 at 20 feet. What's their subtended angle? And Joe standard at 40 feet, what's that subtended angle? And it turns out the distance, if I go from 20 to 40 feet, that is proportional to the ratio of the two subtended angles, right? That's this equation down here again. So if I'm 20/40, I've got 40 is twice of 20. So the thresholds are doubled as well. And it's a linear multiple there, right? So the threshold of detection becomes 1 minute times 2, or 40 divided by 20, and 5 minutes times 2. So I need to get at least this large in order for someone with 20/40 to detect anything at all and to recognize that it's an E, okay? So that's a big difference between our standard of 20/20 and our legal to drive in the state of Texas 20/50, because this is effectively multiply each of these by 2.5. And effectively that means the smallest letter that somebody who's 20/20 can see, we need to multiply that by about 2.5 to get to the smallest letter that we can reasonably assume everybody who's on the Texas road can see. Matters very much for things like how big is the font on signage on the roadway, right? All right. Okay. Now we can calculate visual angle the very precise, very careful trigonometric way. And we can recognize that, let's go with the height of this object and the distance. And if we can assume that with a long enough distance, this is approximately a right angle, now we can use an arctangent, an inverse, I think that's inverse tangent, isn't it? And so we can look at the ratio of the height divided by the distance and do the arctangent of that. And that'll give us the visual angle, the subtended angle. I can also do that for the stroke width. So that's the red one here, right? So if I need to know threshold of detection, I know it needs to subtend at least 1 minute of arc if it's a 20/20 person. So I hope that my visual angle is at least 1 minute of arc. And if I'm saying, hey, can you recognize that that's an E? I need at least 5 minutes of arc to be the answer to this equation here. All right, so we can use this arctangent. You can use it for your homework. It will come out with the correct answer, but there's also an approximation I will always use and I will encourage you to use. And it's kind of an amazing approximation. Go ahead and check it out for yourself. But as it turns out, when you're talking extremely much larger d distance than the height of the objects you're talking about, when there's that big of a difference between these two values, then this ratio, you actually can approximate the arctangent by multiplying it by this constant, okay? And this constant, we can derive the constant. It's basically converting, let me see, it's like degrees into minutes of arc, or maybe it's radians into minutes of arc or something like that. I forget exactly what the conversion is, but 3438 is the conversion factor. And it's 3438 minutes of arc. That's this, this symbol right here. That's for angles less than 10 degrees, not less than 10 minutes of arc. Okay, so first thing I want to point out is don't confuse those two, because 60 minutes of arc is equivalent to 1 visual degree. So we're talking about 60ths of a degree. And so 10 degrees is going to be way larger than anything we talk about in terms of acuity. We're always talking about minutes of arc, which are a fraction of a single degree. And basically this approximation says if anything is less than 10 degrees, which we're well less than it, then this approximation will hold. So for this course, for the most part, I would say, let's use this equation. Also important note, H and D need to be the same units. And it would be very tempting to talk about D in feet, it's 500 feet away, and to talk about E or these dimensions in inches, it's 6 inches tall. But inches and feet don't directly, you need to convert one or the other so that those units cancel out. And then you're left with minutes of arc, which is what you're solving for in the visual angle. Okay, so again, making sure we specify the H and D in the same units, either inches or feet, or could be meters. They end up canceling out, so it's okay. Also recognize, here you go, great thing for me to quiz about. Don't forget that H, even though H stands for height in most cases, H could be the width, or it could be the diameter of a circular object. It should be the diameter of the longest dimension that you're, the smallest dimension that you're attempting to process. So if I need to recognize that this is an E and not a vertical line, I need at least 5 minutes of arc if I'm 20/20 in terms of the subtended lateral width, as well as I need at least 5 minutes of arc for the height. So I like to ask questions where that might get, that might get forgotten. So there you go. If you remember, hey, wait a minute, Ferris might try to trick us if he's only asking about heights and not widths, or if he's asking about widths, we also have to think about heights. Just keep that in mind. All right. So it could be any axis, right? So don't only think H equals height. H equals the smallest dimension I'm trying to either see, threshold of detection, or see with enough detail to identify it, to recognize it. That's the threshold of recognition. So we got an example here. Okay. So imagine I'm driving on the road and I am a driver in Texas. So we know that my acuity is at least 2050. It's 2050 or better. Okay. So that's what this is, how far for a driver, corrected to 2050, to see and recognize what this obstacle is. So I'm not saying, do they detect something at all, which would be a different question. I'm saying, do they recognize that that's a truck tire and not, for example, some tar on the road? So it's something that they need to not hit with their car, as opposed to something that's just part of the roadway. And let's say the dimension that we are trying to, process over is, say the width of the tire, and let's say that's 20 inches. So it's a big tire. It's about 20 inches. So that is our H value. This is what we need to be able to see at a distance D. And so the question is, how big is H? If H is set as 20 inches, what is the value D at which we will be able to see and recognize it? And we know that it must subtend the threshold of recognition. Okay. So we know if somebody is 20/20, we know that's 5 minutes of arc. That's our definition of the threshold of recognition, right? And we know our equation here, remember our cheat sheet, 20 over X can see and recognize an object at 20 feet, that Joe standard can see and recognize at X feet. So again, that's this relation, that's this relationship, remember. So the X there and the X there, we're gonna keep working on that. So we're really asking the question, what must H be, and what must H be in terms of the longest dimension there for Joe 20/20 to see it at 50 feet. So we're really just doing the calculation right now to determine what the threshold of recognition is for this 2050 driver. That's what we're talking about so far. All right, so here's our equation that I showed you earlier, that approximation representation between visual angle 34/38, that's our constant, and then the ratio of the height or the H dimension of the object, and the D, the distance over which you're viewing it. Okay, so this is a true equation. Let's solve this equation for H. So we rearrange things a little bit, we get this, okay? Now with this equation can apply to either of these, H1 and H2. But if we assume these are the same object, then we assume H1 and H2 are the same thing, okay? So if we assume that, now we can equate this half of the equation for this person and for Joe standard here, right? So theta 1 multiplied by, I'm using this equation right here, I'm plugging them in, multiplied by 20 feet divided by 34/38. I didn't put the units in there, but I need to be very careful because I don't want to mix up inches and feet. I want to make sure I'm doing everything right. And this is similarly equivalent to H, double equals to H2. So that's going to be theta 2 times X feet, and again, divided by that same constant. So the two constants cancel out, and I'm left with this relationship. And so that, and you'll notice I could also divide by theta 2, and I'd get theta 1 over theta 2 equals this ratio. And that is where this equation came from. So I just essentially derived it there. But if you want to just work with this and now you can believe me that it works, by all means, go for it, please. All right. Okay. All right, so going back to our example, we got this 20-inch truck tire in the road. We've got this equation we just derived, we just double checked. And now we want to solve for theta 1, which is the threshold of recognition for our 2050 observing person, our driver. So 2050, that's 20 over X, so X becomes 50. And theta 2 is our threshold of recognition for a 2020 viewer, okay? And that's, again, 5 minutes of arc. That's our threshold of recognition, right? So I get recognized, threshold of recognition. And so I'm multiplying that by 50 feet over 20 feet. I get 12.5 minutes. And this tells me a 2050 person needs, their threshold of recognition is at least 12.5 minutes of arc. If it's not subtending at least that much visual angle in its smallest dimension, then we don't have enough subtended angle for this person with this acuity to resolve and identify what that thing is, to recognize what that thing is. Okay. Going back to our equation, visual angle equals this constant times this ratio. And now I'm going to solve for D because that's what we're asking in this problem. We're solving for the distance. And I've got everything I need now. So what is the distance? And we also know the height, that's 20 inches. And we know the theta that we need, that's 12.5 minutes of arc. So plugging it all in, using our proper units now, I get 5,500 inches. I divide that by 12. I get 458.4 feet. So that is the answer to this problem, this example. At about 460 feet away, that will be when our driver, who has at least 20/50 acuity, that is the minimum distance at which they should be able to see and recognize that this object is a tire. It's a busted tire in the road. Okay, now for the next continued example, I would strongly encourage you to read through this, pause it, pause the video, try to solve for yourself based on what you learned. Remember, thresholds are threshold of recognition, threshold of detection. Remember that we have to correct for certain acuity, and remember the visual angle equation and the relationship among multiple angles, for different viewers. So go ahead and pause this, read through, and then you can unpause and I'll work through it. Unpause. Okay, so a couple things to point out. First of all, we have a different acuity to process now. It's no longer 20/50s. They put on their glasses. The glasses don't quite correct them to 20/20, but it's better. So 20/30 now. And assuming there's enough light to still see, I don't want to get into the realm of like we're now transitioning into mesopic or scotopic vision. We're still seeing photopic vision. I just needed an excuse for someone to have to put glasses on, basically. So now how far away is it? And this time I'm not asking, can they recognize it's a truck tire? I just want to know, do they see that there's something there at all? Okay, so if for whatever reason they needed to know, is it a completely clear roadway or is there anything there I have to think about? What's that distance? So I need to be able to, detect the object, but not necessarily recognize it. So now we have a different threshold we're talking about, the threshold of detection. This is the one that's like the stroke width needs to be at least 1 minute of arc. There needs to be at least 1 minute of arc as a gap. Otherwise, it just blends together. And so threshold of detection for 20/30, I am going to trust that you can follow this previous example for how I would calculate that. But we start with 20/20 being 1 minute of arc. And when we have 20/30, the ratio of the two distances, 30 to 20, is 1.5 to 1. And so when we, if we talk about our ratio of visual angles, our threshold of detection for person with this acuity is 1.5 minutes of arc. So that's what's going to go in here. I still know my H here. Let's say it's about the same size. It's still 20 inches, but now I have a different value of theta here. When I plug those guys in, I get 45,000 inches, and that accounts for 3,820 feet. So again, comparing that to the previous one, about 460 feet versus, almost 10 times as much. And that kind of makes sense. I have considerably better acuity, and I'm also asking about threshold of detection, which is about 5 times smaller than the threshold of recognition. Okay, that's all for this one. This is, for the most part, what you'll be working on. This topic and 2.4 will be the majority of the written homework, and I'll explain that in a video and post that as well. All right, tune in next time.